There's a special kind of exponential equation that tends to deal with populations or money called exponential growth and decay. The exponential growth and decay model is the function a of t is equal to a times 1 plus or minus r to the t power. In this model, both of the a's are an amount. The little a that's over here, that's the amount that we start with. We call that the initial amount. The function a of t, that's going to be the amount after a certain amount of time. So you can think of that as the ending amount. Of course, that would mean that time is the t variable. And time can be measured in anything, days, hours, weeks. It doesn't matter. It kind of depends on the context of the problem. The r, that would be the growth or decay rate. Now, you'll also notice that there is a plus or minus in there. Of course, you're only going to use one at a time, either the plus or the minus. And we use the plus when we're talking about growth. And of course, that would mean that when we're talking about decay, we would use the minus. Now, here's a typical exponential growth decay problem that you might see on your SAT, ACT, or MCAs. So Kristen starts an experiment with 75,000 bacteria cells. After 4 hours, there's 23,000. How many bacteria cells can be expected after 12 hours? In order to answer the question, we're going to need the function. In order to get the function, we first need to figure out, are we talking about exponential growth or is this exponential decay? How you can tell is take a look at where you started and where you ended. It says Kristen starts an experiment with 75,000, and after 4 hours there were 23,000. Since that amount went down, we're definitely talking about decay, and the form we're going to need is a of t is equal to a times 1 minus the rate to the t power. So let's come up with our function first. As we go through the problem, Kristen starts an experiment with 75,000 bacteria. That's going to be our initial amount, the 75,000. Then after 4 hours, so 1 minus r to the 4th power, there were 23,000. We want to know how many there are after 12 hours. Now, we can't just take the 12 and plug it in for r, because that 12 is a time, not a rate. So before we can answer the question, we're going to have to solve this equation that we have right now. So to do that, we divide both sides by that 75,000. And that'll simplify to 23 over 75. Over here they cancel, and we have 1 minus r to the 4th power. To get rid of the 4th power, I'm going to use a 4th root on both sides. Those guys will cancel, so we go over to the calculator, taking that 4th root of 23 over 75, and you get 0.744 is equal to the 1 minus r. Now, you could continue and solve this all the way for r, but this actually is a very good place to stop once we get to 1 minus r, because if we were to plug this value in, notice that we have the amount after a certain amount of time is going to be the initial amount, 75,000, times 1 minus r to the t power. And I know what 1 minus r is. It's 0.744. So there isn't really a need to go all the way down to solving for r, because we're good with the expression of 1 minus r. Once I have my function, we're really almost done. Now we can go to answering the question. How many bacteria cells can be expected after 12 hours? Well, that would be the amount after 12 hours. It is going to be 75,000 times 0.744 to the 12th power. Of course, we're going to need that calculator again. When you calculate, you get 2,157.428. Now, of course, we should answer the question within the context of the question. We're asked how many bacteria cells can be expected. And you're not really going to end up with 0.428 of a bacteria cell. So we'll just cut that off and call that 2,157 bacteria cells. Another type of exponential growth is what's called compound interest or compound yield. The formula is A is equal to P times the quantity 1 plus R over N to the NT, which takes a form that's very similar to that exponential growth formula. We have two different amounts here. This P is called the principal when we're talking about money. The principal is just the initial amount that is invested or loaned out. The A that's on this side, that's going to be just the amount that is in the account after a certain amount of time. Now we still have T being time, and R, instead of being just a growth rate, is more specifically an interest rate or an annual yield. But what is important is that that is annually, which means the time has to be measured in years. Now the one extra piece that's in this equation, it wasn't in the last one, are these two n's. All right, now they both mean the same thing, and what that n is the number of compoundings. Now, what we mean by that is when you take simple interest, you would just figure out how many years it's been since the account was established or the loan was given out, and then just calculate that annual interest over that time period. But when we compound it, that means that if you have, say, 12% annual interest is compounded every month, you don't get all 12% in the very first month. And they don't wait until December before they give you all 12%. Instead, what happens is that 12% is divided up equally into each month. So you would get 1% in January, the second percent in February. But once you have compounded the interest, now the account has what you initially put in it, and at the end of January you gained interest on that, and that interest was put into the account as well. Now when you go into February, in February you get that same 1% interest, say, but it's not just on your initial amount, it's also on the amount of interest that you earned in January. On to March, you get the interest on your initial amount plus the interest you earned in January plus the interest you earned in February, and it keeps you gain interest on top of interest on top of interest, and that's what we call compounding. So let's take a look at this compound interest problem. If $2,500 is invested in an account that pays 4.2% annual interest, find the value of the account after 15 years if it's compounded annually. So to set up our problem, we want to find the amount after 15 years. So we're going to take the principal, that's starting investment of $2,500. We're going to add our interest rate, 4.2%, which of course we have to turn into a decimal, 0.42. Since it's compounded annually, that means it's getting compounded one time in a year. So our power is going to be the 15 years times the one time it gets compounded in each of those years. Going over to the calculator, when you calculate this amount, it should be $4,633.99. When it comes to money, you should cut the decimal off after two decimal places. And typically, there's no rounding when you're dealing with money. I mean, a bank wants to keep as much as it's going to keep, so they just cut the decimal off right there. But let's see what happens to that $4,633 when we change the compounding from being compounded annually to being compounded monthly. If everything else is the same, then the amount after 15 years, we're going to start with our principal, and we're going to add 4.2% for 15 years. But when it's compounded monthly, that percentage rate is divided up between the 12 months. It also means instead of being compounded 15 times altogether, it's going to be compounded 15 times 12 times, because that's each month for each of those 15 years. Now, you might think that, well, that must mean that our total amount is going to go down because we cut our percentage rate by so much. That 0.042 got divided by 12. However, remember, this is finding interest on top of interest on top of interest. And when you calculate this amount, you should get $4,688.86. That's an increase of $50 just by having it compounded monthly instead of compounded yearly. Now, if you're thinking $50 isn't really that much, I mean, I let that thing sit there for 15 years to get that $50. Well, it was also only an initial investment of $2,500. If that $2,500 is turned into $2.5 million, then that 50 grows a lot more into something like $50,000, and that is considerable. Now, what happens if we increase that compounding more so that it's daily? Our formula is going to stay very similar. We still start with our $2,500 investment. Our interest rate is still 4.2%, and we're still at 15 years. But instead of compounding it just 12 times, we're going to compound it 365 times. And you might be thinking, well, geez, this should increase it by a lot. You know, we increased our interest by $50 when we went from once a year to 12 times a year. So now what if we increase that by 30 times as well? We should be expecting a lot more, right? What actually happens is we're at $4,693.85. So that increase from monthly to daily, even though we compounded interest a lot more often, remember, we've also cut that interest rate a lot more times as well. It does actually result in an interest that is $5 more, which is an increase, but it isn't as big of an increase as it was from going from annually to monthly.